Let me just quickly introduce Tiago Carrillo Bilo. He has, as a student and still, he basically is focused on meteorology and physical oceanography, which is exactly, in my opinion, what we need to know more about. He got his undergraduate degree in Sao Paulo in Brazil, bachelor's and master's, PhD at the University
Of Miami.
Miami, and it was at the Rosenthal School.
Yes, it was.
Yeah, Rosenthal School, and then went on to Scripps. And he's been at the University of Maine a long time, since September. Right?
Exactly.
So
Since October.
October, yeah.
Yeah.
He arrived late, so no, it's great to have him here. He's obviously going to be talking about, in particular, ocean circulation in the North Atlantic. A lot of the people here have worked in Greenland, so obviously we're very interested in how the Greenland ice sheet impacts ocean circulation. And a lot of us have also worked on the causes for abrupt climate change and millennial scale events. So we look forward to a future talking with Tiago about many of these things and learning more about the physical oceanography involved. So
thank you, Paul, for the nice introduction. Hi, everyone. First of all, thank you for coming today. I know like AGU is happening, you know. I was supposed to give a 8-minute version of this talk in AGU, but for other reasons, and I couldn't. So it's nice that I could bring some of this that might be of interest to some of you. So today I would talk about this is a flashy title, A Fresh Surprise. What did recent observations of the subpolar North Atlantic teach us about the impacts of salinity anomalies on Atlantic marginal returning circulation? Right, this is a mouthful, I know, but so before I start, if you have any questions, you don't understand something I say, just ask the question. For me, it's no big deal. I think I prefer that to have a conversation than I just talk, and I lose you like in the first 10 minutes or so. Salinity anomalies, right? Fresh water. I'm going to talk about a lot of fresh water. I know some of you have been working on Greenland, on the melt of ice sheets, icebergs. I had the pleasure to see Kristen gave a talk the other day, which was really nice. And she worked with my postdoc advisor. That was a surprise, a first surprise. And you've probably seen this picture, or at least a version of this picture somewhere at some point, like global conveyor belt, right? The thermal line circulation, or the most recent name when we start including the wind or the atmosphere in the play, which is the Atlantic marginal returning circulation. We have the global marginal returning circulation, and that's the Atlantic one, right? So here we have only the main pathways. You always have to keep in mind when we talk about the AMOC is it's the integration of all the north-south flows, right? Everything that is going north, everything that is going south. So in a certain latitude, when we define the AMOC, we're talking about the summation of all those currents, all right? In a certain level, in a certain density class of water. And that's how we define those flows. And here we just see some of the main pathways, right? So in the North Atlantic, for example, you can see the red colors here show the most surface part of the AMOC. And in the North Atlantic is basically, I hope I can you see in the Zoom, can you see my mouse as well?
Mm-hmm.
All right, great. So this is the loop current that enters in the Yucatan channel that came, this flow came from the South Atlantic. And as it goes around Florida, it becomes the Florida current, and then it becomes the very known and famous Gulf Stream, right? As it flows northward. Oh, I lost it, mate. And here we have part of the recirculation, part of the subtropical gyre that we call it, and as it continues moving northward, bringing all heat and salt towards the subarctic and subpolar gyre, subpolar and subarctic parts of the Atlantic, it becomes the North Atlantic current. That's what we call it. Part circulates around the subpolar gyre, as we see here. Part moves even north and bringing all this heat all the way to the Nordic seas and all the way to the North Pole, right? We know that. And as soon as it reached those high latitudes, the atmosphere started playing a huge role here, where it's removing a lot of this heat, especially during winter time. This water becomes really cold, and places like the Labrador Sea, south of Cape Farewell, in Greenland over here, we have a lot of the heat loss, and this water becomes very cold, very dense, and it can sink down. And this return flow, and in the Nordic Seas happens the same thing, right? And this return flow, that's the lower limb of the AMOC, has different characteristics, but it brings a lot of the carbon that got trapped in the water, nutrients and other stuff south to great depths below 1,000 meters. So that's what is important, right? The ocean is more like this buffer for climate variability. And I don't have to tell you that you probably already know that all this heat that the atmosphere took from the Gulf Stream of the North Atlantic currents, like keep the weather moderate in Northern Europe, and it controls some of the water patterns in those high latitudes as well, right? And even there are a lot of studies showing this Atlantic water penetrating fjords in Greenland and interacting with the terminal glaciers and helping melting icebergs and glaciers around Greenland as well. So, all right. And I'm going to focus a little bit more now on the subpolar gyre. That's where the OSNAP program is running. It's one of the main projects that I'm involved in. We are in the process of renewing the program for, we hope, for 5 more years. So here we have another schematic of the AMOC as well. I hope we can, in the future, we are working on updating this. But essentially, we have the North Atlantic current, as we saw before, and this current recirculates with the subpolar gyre around the Mid-Atlantic Ridge, around the East Greenland, West Greenland, and Canada coast. And as this superficial flow flows cyclonically, it also cools and freshens quite a bit, right? Some of this water enters in higher density classes, and because it becomes heavier, it's cooling, right? So it moves into the deep layer of, or the deep limb of the AMOC. And the OSNAP program, it's been in the water since 2014, and it's a set of several deep ocean moorings, all right? So all those little red dots are a different instrumentation that we have, measuring usually velocity, temperature, and salinity of the water, right? We have this program in the water since 2014, and it's still going. And the idea is to monitor the main pathways of the AMOC, the boundary currents, essentially, right? And we use other instrumentation to fill the gaps between the mooring arrays to get a sense on the subpolar AMOC. So again, everything that is crossing the moorings and coming out. Remember, it's an overturning, right? So surface flow that is coming over the moorings going northward, or in the case of Labrador Sea, it's a weird situation where it's east-west, but it's moving northward, it's overturning, densifying, and coming back. So that's what we are monitoring since then. And I'm gonna show you some of the results that we got, mostly from the OSNAP program. From the most recent low salinity anomaly that we had. I'm going to talk about what they are and how it interact with the individual components of the AMOC, all right? And how we think they are affecting the AMOC as well. All right. So actually, there's no surprise at all, because salinity anomalies happen all the time. They're a recurrent feature in the ocean, all right, especially in the subpolar gyre. And that's this picture here, this graph shows the average salinity in the upper 200 meters. And when I say 200 meters, that's our surface of the ocean. I know, like, some coastal oceanographers, 200 meters, that's the entire water column, but we are over really deep waters here, right? So that's the very top of the ocean layer. And that's where the fresh water stays, because fresh water, although some of this fresh water can be cold, but it's very fresh. Salinity usually trumps the temperature effect, if depending on the magnitude of the anomalies. So this fresh water can stay right at the surface, right? So that's why we're looking at this region, and that's in the Birmingham Sea. And I put this together for a paper that we're interested in the Birmingham Sea. It's one of the regions that we can have deep water formation, the same class of Labrador seawater, if you heard of it, as well. One of the main water masses of the lower limb of the AMOC. All right. So we were interested in that, and you can see here, if you take all the historical data from several decades and put together like this, you can see the different salinity events that happen along the way, and they're very known. They have been explored in the past, right? Here we see at least 4, and that's the most recent one, at least in the Birmingham Sea. I'm gonna show you that there is some indication of a new one developing as well. And they're recurrent, and they affect mostly what we're interested when something that happens. We're thinking about the ocean stratification. So when we have a salinity drop, you always think, okay, at least in the mind of the oceanographers that are interested in large-scale ocean circulation, is how the stratification is changing. And in this case, a freshwater anomaly can enhance ocean stratification, making the upper water more buoyant, meaning it's harder for the atmosphere densify this water and makes it sink, right? So when something like this happens, we also, okay, what is happening with convection? That is the main process of deep water formation. That's what we are interested in. And one example is the Great Salinity Anomaly of the 70s. That's a very known, and has been studied for the past 5 decades, right? So there's always something new about that we learn about this from several different angles. For example, that's a recent paper from Carrillo and Morrison, shown that only in 2005, although it happened in the 70s, that the freshwater content of this particular anomaly that affected mostly of the Labrador Sea, although you can still see in the data in the Birmingham Sea, had a 10,000 kilometers cube of fresh water. All right, so one kilometer cubed, you multiply by 1,000, so that's 10 to the 8 meters cubed. Then you multiply by 1,000 to get the number in liters, and you divided that by 3.6 to get in gallons. That's around 200 and something million gallons of fresh water in the subpolar jet. That's quite a lot, and it only translates in a few degrees, like it depends on 0.1, 0.3 here, 0.2, yeah, 0.2 in salinity of grams per kilogram in salinity change. And in the Labrador Sea was a little bit more, I guess, right here. So in the Labrador Sea was around 0.4, and that constitutes the lowest salinity anomaly ever recorded in the region at the time. That was described by Bob Dixon in 1998, right? In 88. That's quite a strong change in salinity. And it changed quite a lot of the properties in the Labrador Sea, including the stratification of the ocean, and helped to suppress quite strongly the deep convection in the Labrador Sea, where we have the formation of Labrador seawater for several years. And that changed not only the properties of the waters at the surface, but also at the bottom, because now we don't have this convection happening. You don't have the vertical mixing bringing those signals down or below 1,000 meters, for example, right? So the water that we usually see Labrador seawater when it's formed, and you see all this vertical mixing happening, just stopped. right, for several years. So that's quite some time to make the circulation, bring those signals around, and spread this different water property of Labrador seawater, different flavor of Labrador seawater, right? And because deep convection was suppressed, the convection is much shallower now. So the water that's being produced, it stay in a closer to the surface, and the circulation patterns are also different. So you can see different patterns spreading of those type of waters as well, right? And if you ask me, was the AMOC impacted? Well, numerical models say yes, and there's a lot of numerical simulations exploring this type of phenomena, and how it changed pressure gradients that can modify the velocity structure of the ocean, for example. We've seen that, but we never observed that. All right. So that because it was a time that we didn't have many observations around, only few sparse moorings and cruises that gathered this information for us, we didn't have, we had to look at the models and see what they were showing when we have this kind of phenomena going on. All right. And because of that, the origin, for example, of this anomaly has been debated for decades. Where it came from? Was it from Greenland? Was it from the Nordic seas through the Frame Strait, from the Arctic, or came through Davis Strait with a bunch of fresh water penetrating from our Canadian archipelago, right? And I think finally, after decades, we know that most of this fresh water probably came from Frame Strait, through the Denmark Strait, or along East Greenland, and reached the SUBPOLAR gyre. But impacting most of it, the most impactful in terms of salinity was observed in the Labrador Sea, where all this fresh water ended up being, right? But most recently, we had what we call the most recent great salinity anomaly. And it's a different complete scenario that we had back then in the 70s, because now this anomaly happened where we had the OSNAP in the water. We have programs like the OOI, which has moorings that are integrated in the OSNAP calculations as well. We have the Argo program. If you are not familiar with Argo, they are a bunch of autonomous vehicles that can keep profiling temperature and salinity continuously in the ocean, and they drift with the current, so they are moving around as well, right? We have long-term CTD surveys, cruises that repeatedly go out and take measurements in this region. So in terms of data, we have the GDP, the Global Drifter Program, well developed. Those are drifters that we put in the surface of the water, and it has like a sail, usually 15 meters long, where the currents can push them around, and you can track the currents by GPS, right? So we have hundreds of those floats out there that we can track and study spreading patterns, for example, right? Plus other long-term programs, European programs are out there, and the data is available, right? We have now decades of accumulated knowledge as well about the Arctic and subarctic regions. We know better what their circulation is doing, what the currents are doing, where it goes, how long it takes for things to move around. Plus, now we have all the reanalysis, all the good models for atmospheric simulation to connect with the atmospheric simulation as well, right? And we have better and more powerful numerical models that we can study smaller and smaller scales and see the impacts of these type of motions also in the large space scale picture, right? So it's we are living in a very exciting times to make those studies, I would say. So before I continue, what I'm going to do now, I'm going to tell you a little bit about the story of this most recent anomaly, right? how it impacts what we think it happened and how it's affected the individual components of the AMOC. And I'm going to focus on that because that's where the GOESNAP could give most of the contribution. So this particular anomaly, it has an interesting story because it has a different origin from the 70s, anomaly from the 70s. It's not just a huge freshwater discharge that came from the Arctic and changed the ocean circulation. It's more a diversion of water due to atmospheric anomalies, atmospheric patterns. So what happened was, and that's a paper from Penny Holiday, published in 2020. The atmospheric circulation was in such a way that the fresh water that flows along the Canadian archipelagos and the Canadian coast right here got diverted. That's the Labrador Current, that's what we call it, and was diverted by the winds. And all of this fresh water that was diverted got entrained in the background circulation of the North Atlantic and got carried away, and it got in the North Atlantic Current. And you can see in 2014, in 2015 move, that is this big blue blob over here of 0.2 practical salinity anomaly. And it moved northward in the Iceland Basin, affecting the surface waters in the upper 200, 300 meters. And that was the strongest freshening event in the Iceland Basin in the past 120 years. The 70s, the GSA from the 70s, it had a 0.4 change in the Labrador Sea, but as soon as it moved to other regions, it got diluted and dispersed. So the anomaly wasn't that strong in the Iceland Basin, for example. But in this case, a lot of this fresh water got concentrated in the Iceland Basin. So we have this huge anomaly there. And of course, you can expect that this is spread everywhere, right? It's in the now it's being advected by the ocean circulation, so it can spread quite efficiently by the ocean currents and affect the ocean properties all around the subpolar gyre. We're not gonna get to that. But another interesting take on this is because of this diversion, it cut the supply of this fresh and cold water that was running next to the coast. Usually, and this water usually goes around the Grand Banks and flows over the New England continental shelf. So in case of Maine, after 2012 or so, the Gulf of Maine, for example, became much more saltier and warmer because of that. And there's a relationship here because of the atmospheric circulation. We cut the supply of fresh and cold waters and divert it somewhere else. And instead of moving southward, it got concentrated in the subpolar gyre. And in only a few years, and that's the interesting part of studying this phenomenon, is because in only a few years, we managed to calculate its freshwater content, its causes. I'm going to discuss in a bit. Its spreading patterns, impacts on convection, and other impacts on the ocean circulation, right? In only a few years. The 70s took 5 decades to get to the same type of conclusions that we got in only a few years. So that's the kind of powerful tools we have right now. All right? Good. Okay. So here we kind of use the same color palette from the previous map, right? So blue colors represent freshwater anomaly, right? A low or a negative anomaly of salinity, and red is a positive. That's it. It's saltier. When it's positive, it's saltier. When it's blue, it's fresher. So once this anomaly reached the Iceland Basin, because of the cyclonic circulation of the subpolar gyre, we can expect that it's going to spread all around along those currents. All right, and that's what exactly happened. So if I play this, okay. If I play this in a loop, you can see this freshwater anomaly going around and is spreading along the subpolar gyre, right? And you can see that it can spread really quickly around the edges of the gyre, but this water, it slowly spreads towards the interior of the ocean, where we have most of the deep convection happening, deep water formation happening. And this water gets concentrated and accumulated in the interior of the basin, especially in the interior of the Armenian Sea. And after that, it spread. When we did this paper, we stopped in 2020, but we know for a fact that it continues spreading and diluted across the subpolar gyre. But in the 2020 was the peak of the concentration of this water, freshwater content in the Armenian Sea, which is between the Mid-Atlantic Ridge and Greenland. And we use all sorts of data from moorings, from OSNAP, which are the little stars, okay, and drifters and Argo floats to track and study the changes in the certification of the ocean and the timing of the spreading as well. So we found that, for example, if anomaly, and that's very interesting, if anomaly happens in the Iceland Basin, all right, as soon as it gets close to the Mid-Atlantic Ridge, south of Iceland over here, it only takes 3 months to go all around, all the way to East Greenland. For in the oceanography term, in atmospheric terms, that's quite slow, but in oceanography terms, that's quite fast, right? So in one single season, if you have an anomaly of fresh water in the Iceland Basin, we can get that reaching the other side of the basin and affecting a certification and all the way to East Greenland, right? But that's quite powerful. And it takes a few years, 1 or 2 years for this water, if there is a constant supply of fresh water, source of fresh water, to this water slowly spread into the interior of the Armenian Sea and accumulate there, enough to impact convection, for example. And that's the first impact that we can imagine that can happen. So in the Armenian Sea, for example, where we saw this accumulation happen, this freshwater anomaly helped to suppress deep convection quite a bit. And here what I'm showing is, and just again, the Armenian Sea is right here. And here what I'm showing from more, the gray line is the mixed layer depths from mooring. So mixed layer is one of the metrics that we measure convection, right? Or can have an idea how deep convection is reaching. So you can see that in 2016 and 2017, 2018, convection exceeded 1,000 meters depth, meaning the atmosphere was able to remove heat and enough heat and buoyancy from the water column to make this water mix all the way down to 1,000 meters or more, right? The little green dots are the same measurements, the same estimates, but with all the Argo floats profiles that we can find in the basin. So we want a double confirmation. And in 2019 and 2020, when we have most of that concentration of fresh water, the mixed layer depths barely exceeded 600 meters. So that's quite a change, I would say. And we try to understand, try to disentangle the temperature, the impact of temperature, atmospheric temperature, and salinity of the ocean using a idealized simulation. So those are what the stars and the circles represent. All right. So the stars represent, the circles represent realistic conditions in this idealized simulation. So you can see that it represents quite well the maximum mixed layer depths, while the star represents similar simulations, but now only with salinity changing. right? We kept the temperature of the ocean same, the temperature of the atmosphere the same as well. We only changed the salinity. We just put the freshwater anomaly on. And that's what we got. That's the stars, right? So, oops. Just the salinity itself was enough to suppress deep convection in this case. Of course, it's always a tug of war between the atmosphere and the ocean, right? You get to the end of fall, where the atmosphere becomes really, really cold. So if you have a mild winter, and that also happened in 2019, for example, on top of the freshwater anomaly, we also had a mild winter going on, right? In the ocean. So if the ocean is not stratified enough, it's going to be easier for the atmosphere to mix down all this water. But if the atmosphere is also too hot, that's not going to happen, right? So there's always these different components that are playing a role here. And we kind of managed to disentangle at least the role of the salinity on this, all right? And we saw that it actively helped, or at least helped to suppress deep convection in the Armenian Sea as well. So that's one thing.
Quick question.
Yeah, of
You
course.
said that you keep the ocean and the atmospheric temperatures constant.
Yep.
But these are going on throughout the year, so there's a lot of seasonal variability in the
Right,
area.
it is.
So
Yeah.
how much do you think, if you ran the model, including those, how different do you think this would be?
So that's a good question. In the realistic conditions, we had the seasonal cycle, like changes in the seasonal cycle every. We had that. And in the idealized, more idealized version with are the stars, where we try to keep it constant, we chose a winter condition that was strong enough. So on the average, like what you can expect during the winter time based on historical data. And we only changed in terms of just put the salinity anomaly on. But in the realistic conditions, we do have these seasonality changes every year.
And that's why there are gaps, because you're only really talking about the winter.
Yes. So we're only talking about the winter, and because here during the spring and summertime, the ocean actually gains heat instead of losing it. So that's why there's no buoyancy change in this little model here. Yeah, it's a PWP model. It's 1D where we only, if we put a buoyancy fluxes from the atmosphere, from the ocean to the atmosphere, or vice versa, winds and the ocean stratification, what is the resulting mixed layer depth, or the potential to convect, I would say. All right, so that's what impact on convection. The second one, and I think that's one of the most interesting ones, it's less known, is that there was some quite freshening of the deep ocean or in the layer of the overflow waters. I'm going to explain a little bit through an entrainment process, right? I know this is quite a lot of information here. So the overflow waters, they are formed in the Nordic seas, all right? So they convect north of Iceland, all right? In both sides of Iceland here, in the Norwegian Sea and the Atlantic Sea over here. And here between Greenland, Iceland, and Scotland here, we have what we call the Iceland-Scotland Ridge, which is a sill that separates the subpolar gyre to the Nordic seas. So we have a ridge, we have two deeper basins, all right? So in the Nordic seas, we have the convection forming those waters, overflow waters, and they sink. They fill up the bottom of the ocean, and as this very cold water, it hits the depths of the sill, right, and suppresses that, it flows into the Atlantic, all right? And because it's heavy enough, it flows along the slopes of this ridge and the continental slope right downstream. And it's a gravity current. So it's very turbulent, and it entrails and engulfs a lot of the Atlantic water that is there. as it goes down this slope, and it settles in a certain depth. So that's what this kind of a this schematic is showing. So that's the blue arrows here. And because of that, it can mix with the signals that it's going on in the Atlantic, right? So these waters are constantly being spilled out of the Nordic seas in both sides of Iceland. Here in this schematic, I only show the Iceland Scotland overflow water, but it also happens across the Denmark Strait on the other side of Iceland between Greenland and Iceland. And whatever is going on in the Atlantic is going to end up in that deep layer, all right? So what we've been finding is that if at the time this water comes out of the sill and is starting training Atlantic waters, right, it's going to entrain those properties down to 1,000 centimeters, 2,000 meters, and so on. So it goes straight, this signal can go straight to the lower limb of the AMOC, or the deepest limbs of the AMOC, quite fast in one season, right? And that's what we saw from using the moorings. In a sense that, so these two Hofmöller plots here are salinity anomalies, as I've been showing you guys, from the first few years of OSNAP, 4 years of OSNAP. And in the left, we see in the x-axis here, we have different moorings, all right, in the Iceland Basin, with waters in the upper 300 meters or so, all right? And in the right, we have near bottom salinities, around 2,000 meters or more, all right? And you can see that in one side, here in the left side, in the upper, the salinity anomaly is in the Iceland Basin, got to the M3 mooring, which is right in the middle of the basin right here, in 2015, August 2015 or so, something like that. And and the other moorings not long afterwards, right? Like in 2016, in the early 2016, you could see the signal. In the near bottom waters, it started showing up only in 2018, or late 2017, early 2018, right? Although it seems quite a long time, but in terms of ocean circulation, that was quite fast. And if you take into account the distance between the mooring line and where these waters are formed in the Nordic seas, right? This is the Iceland-Scotland overflow water layer. It takes more than twice that long for this signal to be advected somehow to this back to the line, right? So if the signal is being shown in 2018, is because it had to have another mechanism that could bring this water more efficiently into that layer. And that is consistent if you're taking into account all the propagation time that based on the velocity of the currents that we know, and the distance between where the entrainment happens, where the line is, that's more or less the timing of that, of the travel time of the signal. So it's consistent with the entrainment, bringing these signals down to the water column quite efficiently. And by the way, that happened also on the other side in the Denmark Straits overflow waters. So they are becoming lighter overflow waters for sure. Okay, and that's one of the results on the other side. So what we have here in blue is the transport of the deep western boundary current on the Denmark Strait side, right here, right? So the strength of this current. So if you're not familiar with what this radar is in terms of transport, is 1 million cubic meters per second. That's what it is measuring. All right. So that's the blue line. And between 2014 and 2020, we had a decrease of approximately a 3.5 radars per year reduction. between 2014 and 2020. At the same time, we started seeing the freshening, which is the red line, right? And this is a result because we define the deep western boundary current or the transport in a particular density layer, right? So what happened was because of the freshening, the deep water, so that's transect. So Greenland is one side, the Mid-Atlantic region is on the other side, and the Denmark Straits overflow waters are this fresh water layer right at the bottom, all right? So because we are freshening that, it's becoming lighter, and we usually define Denmark Straits overflow waters as densities larger than 27.88 kilograms per meters cubed of potential density. I don't know if everybody's familiar with what potential density is, but it's just think about density, how heavy it is, right? Let's keep it that way. And it's only in that very thin layer of the ocean here, all right? And we are making the dip of the ocean, the bottom of the ocean there, lighter and lighter. So we are losing area that we are integrating those transports across. So that's why we see that reduction of the transport. We also had some reduction in the velocity as well, but in a smaller degree. And this might be related to the mixing patterns because of a lot of the entrainment and probably the depth of the plume settling down. And it might be slow because it's lighter. It's probably not accelerating as much, but it's still an open question why this is happening. But most of it is because of we're losing area. We're losing a volume of the density water classes. That's it. And that impacts the transport of the AMOC as well. Another impact was on the other side of the Armenian Sea now, and that's the Armenian, looking at moorings on the other side here, or in the west flank of the Mid-Atlantic Ridge, right? We verify that this water also mixed vertically quite fast. So those are salinity changes, anomalies using from different moorings. So we found that this the convection that happened, although it was weaker, it still managed to mix down some of the signal to deeper depths, right? Lightening the upper and intermediate layers of the ocean between the surface and 1,500 meters or so, right? But also, depending on the timing, the strength of this current is defined. It's also a function of the pressure gradient that we can find between the boundary along the Mid-Atlantic Ridge in the middle of the basin. So what is happening is that because we're changing the density of the entire water column, we're also changing how tall it is, right? It's taking more space, and that generates a high pressure in one side, and that changes the pressure gradient and also the acceleration of the currents, all right? So this is also happening. And what about the Labrador Sea? Well, this anomaly probably dispersed quite a little bit after 2020 and mixed down at different components of the AMOC. But more recently, Igor Yashayev, looking at the data across the Labrador Sea, and that involves historical CTD data, Argo floats in this along this AR7 line over there. And I'm not gonna bother you guys with all those panels, but what he found that is after 2021, the atmospheric conditions allowed a lot of fresh water to be discharged from the Arctic through Davis Straits. and dumped a lot of fresh water in the Labrador Sea again. So probably another great salinity anomaly forming, and the cycle repeats itself, right? And that's what we're seeing here. For example, after winter of 2023, and that's the bottom panels here, you can see this purple area here, and this deep blue is where the Labrador seawater formed that year accommodated. Usually it goes down to 2,000 meters or even more. But in 2023, because of the atmospheric conditions, plus all this fresh water that was available, it quite weakened the convection in the mixing, the vertical mixing, resulting in very fresh and cold Labrador Sea near the surface, right? And how this anomaly is going to move around, well, that's what we need to stay tuned to the observations to see what's going to happen and what the impacts on the downstream of the AMOC out of the subpolar gyre. All right. So if you look at the AMOC now, and now I'm going to talk about the AMOC. I'm almost done with the presentation. So now, if you look at the metric of the AMOC, and we measure the AMOC by the maximum transport in a certain layer. So let's say here, usually in the subpolar gyre, we measured along isopycnal surfaces, so along density classes, right? So if you integrate all those currents in certain density classes, right, and then use this density space as your vertical coordinate, and you integrate from the surface all the way to certain density. At some point, we're gonna everything that is moving northward is positive, everything that is moving southward is negative, right? You are integrating a lot of positive stuff, a lot of positive currents along this line to get to the maximum, and below that, it's where the net flow is moving southward, and that's the depth or the density of maximum overturning, and that's the main strength and the main metric of the AMOC that modelers and oceanographers use to measure the AMOC everywhere, right? And that's what you're showing here in black, right? So that's the OSNAP record. And if you look at this main metric, don't bother with the other lines, just look at the black one. There's no trend. There's a bunch of variability, of course, but there's no trend. We cannot see anything here, at least not yet. So if you think about, all right, we have salinity anomalies happening, which is dumping a lot of fresh water, increasing certification, decreasing convection. When we think about it, and you think about how the thermal line circulation works, and all the hosing experiments that a lot of people have been exploring in the literature, right? You expect some reduction, right? A slowing down of this overturning circulation. After all, that's the driver, right? This water that's being formed is not moving and making the overturning conveyor belt works, right? But that's not happening. So we are in the process of understanding why. We saw there is impacts. There are a lot of impacts in the individual components of the AMOC. But when you get the main metric, that doesn't translate to observable impact, right? And that's because we usually, it's how we define the AMOC. And that's one example that we can see, if we define it slightly different, we can see some of the impacts going. So from this paper from Coleman and et al. In 2024, what we found out is that if you use the main metric, no statistical significant trend in the AMOC. But we use a fixed density layer to track we always pick the maximum strength of the of the AMOC to define the AMOC. So it's changed every time it's changed a little, it's changing a little bit the maximum overturning. We always pick the maximum overturning, all right? And that's for all sorts of reasons, all right? But when you do that, you lose the signal. Now, if you choose you let if you choose a certain isopycnum and you fix the isopycnum, you just don't follow the maximum strength. You just look at the transport of the AMOC in that particular between the surface and that particular density class. That's where we have the signal, because the upper ocean is becoming less dense, or the deep ocean as well, depending on the time, right? So what's going on is we're changing certain density, the transport in certain density classes. So if you choose, for example, the average density of the maximum overturning and get the transport on that particular density, that's the red line. And that's decreasing, because the transport in that particular density, it's decreasing because it's moving to another density class. There's transport being added to another density class, lighter in this case. All right, so that's what's going on. So it's if you define it in a slightly different ways, you can capture some of those signals, and really depends what you're trying to study, just to define how we're going to define that. And after all that, I'm almost done. Those are the three main takeaways that I get from all of this. One is definitely living in exciting times of physical oceanography and climate science, because now we can observe in quasi real time signals, and like here I'm calling climate signals, because we are only looking at a salinity signal there. But if you think about now in the main modes of variability of the atmosphere, like NIO or the East Atlantic pattern, for example, they are also imposing changes to the circulation and the water properties. And they can move in a similar fashion to the different limbs of the AMOC, right? Through the same processes are happening all the time. So we can in quite real time, can observe climate signals impacting the ocean. And although it can be scary, because we know what's going on, but it's also very exciting because we can learn a lot of stuff. And they seem to be training the ocean much faster than we thought. Instead of like decades or hundreds of years, we know this can happen in a single season or in a few years, right? That's very fast. Great salinity anomalies like phenomena significantly impacts the individual components of the AMOC. Although it doesn't always, it impacts the basin-wide AMOC, because there are compensatory phenomena happening at the same time, but it can have a significant impact. And those signals are going to propagate somewhere down the line, downstream, all right? Although the full picture of how we understand the signals traveling around the system is still incomplete, and there's a lot of work to be done. Oops. And finally, where's my third one? I don't know why it's not showing. Where is my third one? Okay, I have a third one, believe me. It's not showing. Okay, but I will read it to you, right? For some reason, it's not showing in the slides. We do expect downstream changes on the AMOC, all right? All the way to tropical regions and maybe South Atlantic. Now, the amplitude and timing are still open questions, all right? And how those signals propagate and impact the structure of the ocean currents downstream. But we do expect, in some degree, that's the point. And with all this data, all the apparatus that we have and the multiple monitoring lines of the AMOC that we have in place right now can help us understand the timing and the amplitude and the impacts of this of those signals. And yeah, that's all I had. I hope you learn a little bit what my interests are, and if we have time, feel free to ask some questions.
We do.
All right. Yeah.
No, great. So because things are, you have the ability to change so fast, you know, just taking like, for example, the Iceland basin, the freshening that shipped.
Mhm.
I am very far from a photographer. How detailed is the fishing industry in terms of their catch in the earth? Changes like these, are they impacting fisheries, and
Mhm.
are you potentially able to use detailed fishing records to kind of either recreate historical processes or use it to
Oh.
your benefit in the future?
That's a good question, and way out of my expertise zone. But I think we first need to understand the current changes and how it's affecting the current fish stocks. I would say one of the things that would be really interesting to see, or trying to understand what is controlling the Gulf of Maine, for example, what is controlling the water exchanges between the open ocean, that's everything that we talked about, in the coastal ocean, and how they are connected, and see how, for example, the dog lobster fisheries would be impacted by this. We know since 2012, the Gulf of Maine has warmed quite a bit. And I think part of the story is tied to this atmospheric circulation that diverted all this cold and fresh water from the New England continental shelf. But that's a pretty good question. I have no idea how to answer that.
I'm curious. So OSNAP, it's approaching its 10-year mark, right?
Yep.
So I'm curious if there's a continued funding and maintenance plan for it, or
We're working on that.
yeah,
Yeah.
if it's to go towards because I know there's also, beyond just the mooring network, there's also, when ships go out on cruises, there's also I guess data points of convenience that are collected, if it's going to move more towards cruise ship based, or deploying more of these moorings. And I'm just curious what the future of OSNAP looks like.
Yeah, that's quite uncertain, but we are working on the proposal right now to extend the mooring measurements for another 5 years, or two more deployments, for 4 years of deployments. And but the idea, together with the new records, is to keep finding new ways to optimize the array somehow, for several reasons. The main thing is cutting costs, of course, but also having more innovative ways of getting the same information or other information that can complement the measurements that we already have. So we have quite a important component of the new proposal on that sense, I would say.
Were there any regions that you want to newly instrument after getting all this data, that there's just some areas that you're like, oh wow, this is far more important than we thought it was, and it's kind of on the periphery of the network? Or did you guys?
I think we covered the most of it. I think our main, I think if I would say there is a Achilles heel of the OSNAP, would be next to, like in the shallow ocean over the continental shelf, especially near Greenland, and where it's really hard, especially East Greenland, where we have a lot of sea ice and a lot of icebergs coming out. So it's quite challenging. Fiamma had a lot of moorings destroyed.
Yes.
Because of that. But we have ways of estimating what we are missing. But most of it we're capturing. we hope to get at longer time scales now. As we pass the 10-year mark, we can start looking at decadal time scales, which is really exciting when we start putting climate variability on the record, and that's pretty cool. Cool.
Couple of quick comments in that question. If you take a look at the paper that talks about the Gulf of Maine being the warmest
Yep.
at this point, it's true. If you look at the long-term record, they don't publish the long-term record. You look at the long-term record, however, you do see that there were warmings in the past.
Oh, okay.
Which is important to think about.
Mhm.
That
Yeah,
does
yeah.
not take away from that. The other thing is that this time when you see the water flow or that the beginning of the 2014 anomaly, that's also when you get a tremendous intensification of the blocking high over Greenland. It has a
Mhm.
lot of effects on Maine's precipitation for one thing.
Okay.
And then the third one was the question, looking at your really detailed data, there was one time I realized it was very short, and I realized that it's a spotty set of measurements. I'm used to that and the stuff I do too. But it was a really remarkable drop in one of the data points there. And I was wondering if you got any information from that, or if it just happened to be that it captured the edge of something.
Okay,
Go back.
which data point
Go
you're
back a little bit farther. I know we're running out of time, but you showed
Yeah, it's right at the beginning, right here.
yep, right there. The
Right
one
there.
That looks like it's about 2019, yeah.
Yep. Well, that is a problem with this particular reanalysis that I'm looking at right here. So the black line is it's I think it's it's the EN4 data set.
Mhm.
So the green is just the low pass filter, and then before 2004 here, before Argo era, is just annual averages. But the N4 here analysis has some problems in terms of their optimal interpolation process. It generates those bizarre things here. So in this case, we had to use like multiple products to see what was real, what was not. And unfortunately, this one that's not real, unfortunately. But yeah.
Understood, no problem.
Oh, I had a lot of problems convincing one of the reviewers in that particular
Keep
paper.
it in there.
And look, we know that's problematic. That's why we use a bunch of other products to make sure we catch what is real or what is not.
But one more quick question, and anybody who needs to leave, please leave.
My question's about this data set as well. So if you look, way back to 1960,
Yep.
and then moving forward, there's quite a bit of variability
Mhm.
with these anomalies superimposed.
Yep.
Then from like 2005 to 2015, there seems to be a time of relative stability.
Yeah,
What's
that's
going on there?
we have more data. I think the uncertainties and the weird variability there, I think, is because of the coverage and the problems with the sparse data before 2004. I think that's the main reason. Maybe it's not all the story here, but I think that's the main reason.
Okay.
Yeah. Because after 2004, the Argo array became quite dense. We had a lot of those floats out there, like taking a lot of measurements. So we got the variability much better. Yeah.
Wonderful, thank you for taking.
All
the
right,
time to
thank
speak to us.
you.